Here we talk about square roots. It's a strange name, square roots. I mean, plants don't have square roots. Never mind. So, okay, we start off with a square. It has an area, A, has a side, S. For some reason, the side is also called the root, whatever. So, area A, side S, area equals S times S, S squared. Now, that gives you A given S. We want to find S given A. Well, we say this, S is the square root of A. So to mean that equivalently to that. It looks, you can see this kind of a letter, funny shaped R, kind of covering over A. That's the notation. I'm not real fond of it in certain respects because it's all open over here and it's easy to write something here and it looks like it's inside. So watch out. Anyhow, square root of A is the solution to root A squared equals A. Now, mind you, there's going to be two solutions. 2 squares to 4 and negative 2 squares to 4. So both root A and minus root A will square to A. But we'll take that as the positive solution. So, okay, here's S, and A is S squared. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Now, to find S in terms of A, you just take this table and flip left for right. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, but oops, square root of 2, well, this is the notation, root 2. Square root of 3 is what? It's root 3. But, well, okay, you can find out if you have a calculator or like this, or you use your phone. Your phone will probably have a calculator on it. If you turn it sideways, it turns into a scientific calculator with a square root. Mine does anyhow. And that way you can find that, punch a button and get that root 2 is about 1.41421356 forever. And root 3 is about 1.7320508008 going on forever, endlessly, never repeating itself. Unlike a ratio of integers, these do not wind up in a infinitely repeating pattern. They're what are called irrational numbers. I can go on about the history of that name. Basically, when they first found out about that these aren't ratios of integers, they got scared, but never mind that. Anyhow. All right. If A is already the square of a rational number, then root A is P over Q, a rational number. If it's not the square of a rational number, then it is not a ratio of integers. It's irrational. If A is less than 0, then root A is not at all on the real number line. The reason why is that if you take a positive number and square it, you get a positive number. 0 squared is 0 and negative squared is positive. None of these are negative. So the square root of a negative 1 is neither positive 0 nor negative. We have to invent a whole new number, actually, a new kind of number, which is, it's not positive and it isn't negative, sort of at right angles to both positive and negative. I think we'll be have time to go over that at the end of the class. And also there is a extra credit set and tutorial, well, extra credit set about the complex numbers in the extra credit module. In general, the square root of a square is the absolute value, because this is always a positive root. Right. So square roots and squares will pretty much cancel each other out for positive numbers. For negative numbers, there's that flip. Now, one more bigger uses of the square root is in the Pythagorean theorem. Pythagorean theorem says a given a triangle with a right angle, a 90-degree angle at this corner, then this side is A, this side is B, the diagonal C, A squared plus B squared equals C squared. Now, there are any number of fairly fancy proofs of it. Here's a fairly old and pretty intuitive proof, I think. You start with this triangle and make 4 copies of it, like this. Here's A and B, here's B, here's A and B and A and A. So these are four triangles fit inside this big square with side A plus B. As you can see, they're the 4 triangles, and then this is a square with side A, so its area is A squared. This is a square with side B, so its area is B squared. Now what we do is we take these 4 triangles, we rearrange them in the big square. Put this here, this triangle here, this triangle here, this triangle here. You're still inside a square with side A plus B. So the areas are all the same. Because if you did a bit of geometry will prove to you that these are right angles. So this is a square and its side is C. So this area is C squared. Now the big squares are the same. The four triangles are the same. So the remaining square areas must be the same. And here's A squared, here's B squared, and they add up to the same area as this, C squared. A squared plus B squared equals C squared. Okay, that's a classic proof. There are more rigorous ones, but this I think does fine. Now, since A squared plus B squared equals C squared, you take square roots, then C equals the square root of A squared plus B squared. To find A, you first subtract B squared and take a square root. Get A equals square root of C squared minus B squared. Similarly, if we start from here and subtract A squared and then take a square root, you get B equals square root of C squared minus A squared. So here are three formulas. This is the one everybody easily remembers. Here you have some subtractions. All right, now, so there are some fairly classic examples. Here are classic right triangles. 3 squared plus 4 squared is 9 plus 16, which is 25, which is 5 squared. The 3, 4, 5 right triangle. There's also a 5, 12, 13 right triangle, a 20, 21, 29 right triangle. In fact, there are infinitely many such triangles. But none of them are have side 1, 1, and root 2. Here's a distance formula. Given 2 points in the Cartesian plane, x1 by y1 and x2 by y2. What is the distance between them? Well, we draw this right triangle with this side parallel to the x-axis, this side parallel to the y-axis, and since these meet at right angles, so do these. The length of this side is the difference between the x-coordinates, x2 minus x1. The length of this side is the difference in the y-coordinates, y2 minus y1. We have the triangle. So d squared equals x2 minus x1 squared plus y2 minus y1 squared. And so solving, d is the square root of the sum of the squares of the differences of the coordinates. That's 4 ofs in a row. Square root of sum of squares of differences of coordinates. Anyhow, that's the formula. So we start off with some examples. Square root of 400. Well, 400 you can check is 20 squared. And so its square root is 20. 9 25ths. Well, 9 25ths is the square of 3/5. The square root of 3/5 squared is 3/5. Square root of n to the 12th. Well, the 12th power is the square of a 6th power, because 6 times 2 is 12. And the square root of a square cancels, and we're left with n to the 6th. In general, the square root of an nth power is x to half that power, with absolute values if there are assignment issues. They say if n is odd or whatever, or if x is negative. Anyhow, square root of x to the n is x to the n halves. So in a sense, and we will make this literal later, a square root is a 1/2 power. You have square root of 64, b to the 4th. What's that? Well, 64 is 8 squared. B to the 4th is b squared squared. Square root of that leaves 8b squared. Here we have a triangle with sides 15, a, the unknown, and 17 diagonal. What's a? Well, a squared plus 15 squared is 17 squared. Transpose of 15 squared. A squared is 17 squared minus 15 squared. And so a is a square root of 17 squared minus 15 squared. And if you work this out, that's square root of 64, and that's 8. This is an 8, 15, 17 triangle. Here we have a triangle with sides 45, b, and 53. Same deal. B squared plus 45 squared equals 53 squared here. Transpose of 45. B squared equals 53 squared minus 45 squared. So b is the square root of 53 squared minus 45 squared. So b is the square root of 784 if you do the math. And the square root of 784 turns out to be 28. And that's b. Oh, I'm sorry. Did I redoing this? I'm sorry, redundant. We have 2 points, -2, -8, and 3 by 4. What's the distance? Well, it's the square root of the sum, the squares of the difference. -2 minus 3 here, -8 minus 4 here. This is -5, square that. This is -12, square that. -5 squared is 25. -12 squared is 144. These add up to 169. So D equals root 169, which turns out to be 13. This is a 5, 12, 13 triangle. Find the distance between the points 9 by -1 and 7 by -6. Okay, square root of sum of squares of differences. 9 minus 7 here, -1 minus -6 here. So that'll be 2 squared plus 5 squared, that's 4 plus 25 is 29. So the distance is the square root of 29, but since 29 is not a square, this will be an irrational. Approximately 5.385, but the expansion goes on endlessly. This one talks about a baseball diamond, which of course is just a square rotated 45 degrees. It's 90 feet on a side. What's the distance between home plate and third and second base? Well, this is a right triangle, side 90 and 90. So D squared is 90 squared plus 90 squared. If you take a square root and do some sums, D equals the square root of 116,200, which comes out to about 127.28 feet. Okay. That concludes this.